All right, so we want to look at what happens when our data has the same mean, median, and mode. And so to do that, we actually have to look at other ways that the data can be measured. So what I'm going to do here is I'm going to put up, again, these are the examples in the lecture notes, but two corporations that hire graduates, and their starting salary in thousands of dollars. What we're going to say is these two corporations both hired 10 graduates, and this is the distribution of their starting salaries. 741. And so, okay, there's Corporation A. And I think I will do in green on the other side Corporation B to distinguish between the two of them. And again, they both hired 10 people, and we're going to look at the data from the 10 people they hired. So here, let's see what we have here. We have 40, comma 23, comma 41. And remember, these are all in thousands of dollars. So that's a $50,000 a year salary. That's a $49,000 a year salary. But we don't need to repeat the word 1,000 or do the numerics of 1,000 behind all of this, because if we know it's being repeated, we'll just focus on the numbers that change, and that can help us just save space and logically deal with our data. All right, so what I'm going to do here is I'm going to enter Corp A onto my calculator, and I'm going to find the mean, the median, and the mode. Well, right off the bat, I can see that 41 is the mode. So I'm going to say the mode for this one is 41. Looking at Corp B, notice 41 is the most repeated, so the mode here is 41, the most repeated. But let's get an idea of the mean, median, and mode of each. So I'm going to come over to my calculator. And I'm going to go into Stat. And I'm actually going to double check my lists. I don't have anything in my lists here. So I'll go to Stat, and I bring up my first list. And I'm actually going to enter Corporation A in list 1. So that's 41. Enter. And I'm just going to work my way through all the data entry items in there. I won't list one out. I'll just double check myself on my list as I add them all across. Let's see. 41, 38, 39, 45, 47, 41, 44, 41, 37, and 42. So there's Corp A. I'm going to go over to list 2, and I'm going to put Corp B in list 2. So I'm just putting all my data into the two different lists so I can keep track of it. $49, $32, $41, let's see, $32, $29, 52, and 58. And I'm going to go back to Stat now. And I want to calculate. I want to calculate one of our stats. I'm going to do it on list 1 first, which is Corp A. And that gives me a mean of 41.5. Let me come back over here. And we'll record that for posterity's sake. We have a, whoops, I don't want a green one. Trying to keep them separate. So we have a mean of 41.5. And again, I'll look back over here on my calculator and I'll come down and I have a median of 41. And so a median of 41. Well, let's look over here. Let's do the same thing for this. Let's find x bar, our mean, and our median. Now, by putting these two lists in here, I'll come back to stat. I'll go over to calculate. I'll do one var stats. But instead of doing list 1, I'm going to do list 2. So second and 2 gives me list 2. Come down and I'll calculate. I get a mean of 41.5 and a median of 41. So a mean of 41.5 and a median of 41. And so these corporations seem to have similar central tendencies. And yet, just casually looking at them, they look differently. So let's try to find some more information about them. So one of the things we're going to look for is the range. And we talked about the range when we were finding class widths. What we want to do for the range is we want to take the max minus the min. It gives me the values that these distributions are spread across. And so for this one, the maximum is what, 47, and the minimum is going to be, is it 38? Do I have this still on the screen? Yeah, good, okay. So let's see, the maximum is 47 and the minimum is 37. Sorry, there it is. I thought. So 47 minus 37. Right, we came through here. 47 was the max, 37 was the min. And so this has a range of $10,000 from the highest to the lowest. Well, let's compare that to Corp B. So the highest is 58. And the lowest was, let's see, what is the lowest running here? 23. And so 58 minus 23 gives me 35. And so this data covers a different amount of our space. This is spread out more. This is spread out less. Well, let's see what that looks like. Let's draw a histogram here. We're not going to go through the construction of the histogram where we construct everything like we did for the frequency tables. Not because that's not how you do it, but because I want to display this. I don't want to talk about creating it. We can create it. That's something that we're practicing with our frequency distributions and creating histograms. But for right now, I just want to look at the results first. So I'll do Corp A and Corp B. Now, because they go through different ranges, we're going to use the larger range to describe our space. So we're going to cut this into 6 bins. 1, 2, 3, 4, 5, 6. And so the midpoints are going to be 25.5, 31.5, 37.5, 43.5, 49.5, and 55.5. And we're going to do our counts up by 1, 2, 3, 4, 5, 6, 7. And so this one has, in this bin, goes up to 6. So right here. oops, get my bins right. So I put all my midpoints, so I need to, you know what, I can actually use a ruler here. Let's use the ruler. Midpoint to there. Midpoint to there. And that's neat when you use the right tools. And this one goes up to 3. So midpoint to there and midpoint to there. And this one goes up to 1. And so that's the distribution for corporation A. It's centered. It's tight around the mean, the median, and the mode. Well, let's use the same scaling over here. And so this is 25.5, 31.5, 37.5, 43.5, 49.5, and 55.5. And again, we'll go up by ones. And that's all we're really going to need to do here. And if we look at that, the first bin here goes up to 1. Second bin goes up to 2. The third bin goes up to 1. This fourth bin goes up to 2. Fifth bin spikes at 3. And the last bin peaks at 1. And so the way the data varies from the midpoint, median, and mode is different for the two. And so like we have done with everything else, the idea for mean, median, and mode is we try to put a number to central tendency. What we're going to try to do here is put a number. We're going to try to quantify how these things are spread out and what it means to spread out. And so what we're going to do is we're going to look at variance. And what we're going to do is compare each piece of data to the mean. Now we're going to do Corp A by hand, and then I'm going to show you how to do it on the calculator for Corp B so that we can compare the two. And so the idea that we want to look at is we want to think of each piece of data. If I come over here and I know my mean is around here, then in one piece of data in here has a distance away from the mean. It has some variation away from the mean. And so we want to kind of quantify that. And so the first thing we're going to define is just a deviation. Now, the book uses the word deviation of x for the data. What I'm going to do is I'm going to do the deviation of x. And this is the same, be it population or sample. So the way we know the difference between the two is we have the individual piece of data I'm looking at minus the population mean. And this is going to be called the deviation of that one piece of data of x for the population, for population. Now mathematically the same thing happens for a sample. We just use different Roman versus Greek letters to distinguish between the two. And so the deviation of x for a sample is, I'm going to use a lowercase d of x, is equal to the individual point minus the mean. Now what's really important is the thing we're going to do right now is why we keep the Greek letters and the Roman letters different, because there is a difference that comes up between a population and a sample, and we're going to have to recognize that difference. So for right now I'm going to treat these two things as a population. These two companies found out all 10 people. That was all 10 people. It's not a random sample. It is all 10 people in the two companies. Now, what I can do is I can look at each piece of data. So I'm going to write it in a column here, and then I'm going to look at its deviation, how far it deviates from the mean. And so let me grab the data from Corp A. Again, I'm only going to look at Corp A right now, and we'll do Corp B by the calculator, and we'll compare the calculator to by hand. This is one of those calculations that you shouldn't have to do by hand that often. For meaningful statistics, we need large data sets, and this is pretty tedious. We only have 10 pieces of data here, and you'll find that this is a pretty arduous calculation with just 10 pieces of data. So 1, 2, 3, 4, and I'm halfway there. All right, so now if we remember, the mean was 41.5. So, oops, and I'm going to clean this up. I'm assuming it's a population, so I'm going to use a population mean. So it's not a standard, right? It's not X bar, it's mu. My apologies for that. And so mu for both data sets was 41.5. And so what I need to do here is I need to take x, and I need to subtract from it 41.5. And so I get negative 0.5. And then 38 minus 41.5. Now I'm not going to plug each of these in. I've got a calculator off to the side, so 38 minus 41.5 is negative 3.5. 39 minus 41.5 is negative 2.5, and so on and so on. Notice there's positive and negative directions. Our data is falling on either side of the mean, giving positive and negative values. So 47 minus 41.5, repeating. And 37 is negative 4.5 and 0.5. Now notice something here. If I sum up all of my deviations, so I get negative 0.5, that gives me negative 4, negative 6.5, negative 3, positive 2.5, positive 2, positive 4.5, positive 4, negative 0.5, 0. They add up to 0. In a symmetric distribution, and a distribution that approaches normal, the deviations will always add up to 0. Just as many things are on the positive side of the mean as are on the negative, and they're spread out in equal distance. So if we want to make the deviation mean something to us, if we want to talk about the distance each piece of data is for the mean, which is what this is saying. This is distance, how far from the mean I am with direction. We have to get rid of these negative signs. And the easiest way to do that, and something that's borrowed from the distance formula, is we square it. That turns this into positive values. And so negative 0.5 squared is 0.25, and 3.5 squared is, and so I'm just going to square these on my calculator. And 12.25 again, because we repeated that number. 30.25. And we've repeated this number, so I can repeat my calculation there. I already did 2.5. That's 6.25, 0.25. Haven't had a 4.5 yet. And that's 20.25 and 0.25. And so now I have all of these squares. So I can come back and I can sum up the squares of my deviations, or the sum of the squares. And that's 88.5. Well, what's nice is I can kind of talk about the distance each piece of data was from the mean. Well, if I have multiple pieces of data away from the mean, maybe I should take the average of that. And so the formula that comes out from this is that if I sum up the squares of my deviations and divide them by the number of pieces of data, I'm going to get what we call our variance. And this is an average of how far, and we're going to use a sigma squared for variance for a population. We'll use something else for a sample, and you'll see that in a minute or in the next video. And so this becomes the average square deviation from the mean. Notice I'm finding out how far each piece of data is from the mean. I add it up and divide it by the number of things. So I'm getting an average distance my data is from the mean, or how far on average it has spread out from the mean. Well, we can take the square root and get this thing called sigma, which is the standard deviation. And this is talking about what the average actual distance is. Well, not actual, but the average distance each piece of data is from the mean. Now notice Greek, this is for the population. So this is the population standard deviation. And it's a way of saying, hey, each piece of data is so far from the mean that I'm spread out. It pegs it into a number. Now some things to notice about this is measured in the units of the things I'm counting. And so if this was dollars, I get dollars squared divided by the number of things. And I take the square root of dollars and I get dollars. So standard deviations have the same unit as what you measured. And that's going to be really important for us to have things that have the same unit. They become a nice measuring device for us. All right, so in Corp A, it had a standard deviation of the square root of 88.5 divided by, well, we had 10 things, which is the square root of 8.85, which is, well, if I round, approximately 3. I think I got like 2.97. And so Corp A has a way of measuring how wide it is, a thing we call the standard deviation of 3. Let's use our calculator to look at Corp B. So I'm going to come back over here and put the calculator up. I'm going to come back in, and we're going to go to Stat, and we're going to calculate again. We're going to do one var stats like we did before. Now remember, Corp B I left on list 2. Come in and calculate. Notice it calculates all of these different things, but right here, there's a standard deviation of x, and it's 10.5. So the calculator has calculated the standard deviation of a population. And so for Corp B, coming over to Corp B here, there we go. Corp B has a standard deviation of 10.5. And so let's come back and look up the graphs here. We've got the same mean, median, and mode, but this has a standard deviation of 10.5, and this has a standard deviation of 3.0. And so the smaller the standard deviation, the tighter the data is towards the mean. or the average distance the data is from the mean. If it gets smaller, everything gets closer. And so standard deviation is the average distance each piece of data is from the mean. All right, so notice this strange calculation we have. Again, we have a sigma, which means we sum up everything in a column. And so when you looked at how I calculated by hand, I figured out what the deviation squared was, and I added up everything in its column. And that gave me the numerator here. And then I divide it by the number of things in it. All right, the technique for a sample is the same, but there's one significant difference. And you should see this in the equations in the front of the book, and you should see it in the equations in the book. So a sample standard deviation, or a sample variance, right, we're going to use an S because it's a sample, not a population, squared, and this is a lowercase s, is equal to the sum of the sample variances, so that's x sub I, x bar squared, divided by n minus 1. Notice this minus 1. And the reason we do this is because as I'm doing a sample, well, I can always gather one more. Because I don't have the population, I could always go out and grab at least one more thing. And so this says, hey, you don't have everything. And so the sample standard deviation is a lowercase s, and it's the square root of the sum of the sample variance, or deviation squared, divided by n minus 1, because I can always go out and do one more thing. The form of the calculation is the same, but we have to realize that this is the first thing where we have mathematically been different between the sample and the population. If I come back and look at my calculator, when I do my stats, it lists the sample here with an S of x. And notice the sample standard deviation is slightly bigger than the population. And that's due to the I might have one more thing going on. And so these are ways that we can measure how data varies within a space.